Kalimera. Hi, this is Ahmed Wahid. I am Rosmus Munder's SmartNet student. The topic of my presentation is 5G New Radio, the new wireless interface in 5G network. As the number of mobile user and other electronic products increasing day by day, so it is very important to increase the capacity of the system, coverage area, and also the performance of the system. So a lot of research going on in this research area. 5G new radio is one of the technique, and in this presentation I will discuss about the content, 5G new radio and air interface, what are the spectrum range and carrier aggregation, and what will be the advantage of advanced beamforming technique, and then new radio numerologies, then the protocol stack, and after that, in the last part of my presentation, I will discuss about what are the testing required when you deal with the very high frequency, and what the issue uh, when you implement this new radio, what issue we can face, and in the end, what are the infrastructure cost, and what innovation we required if we want to implement this new radio. So here we go, the 5G new radio. So we discussed mostly about the three emerging uses cases. For example, enhanced mobile broadband. If you talk about like peak data rate, you need 20 gigabit per second, and area traffic capacity up to 10 megabit per second, and also network energy efficiency is 100 times. So definitely your choice will be, you need to enhance the capacity of the system. There are some example also for in 3D video, you need high data rate, high capacity, so you can implement on this part of the 5G of the triangle, you can say. The second is massive IoT, like you need a connection, one device is connected to another device, and also if you talk about the major application is sensor. For example, when you talk about sensor, maybe sensor delay the values, we don't need high, maybe latency can be high, and we don't need much capacity for this. We just need that a lot of devices connected with each other, and we like receive the values so that we can make decisions. So massive connectivity is needed in this. And in the third part of the triangle is low latency. For example, if a robot is performing a medical surgery, so latency is very important. For example, latency should be very less, around 1 millisecond, otherwise it will create a problem. So these three cases can be implementing by using a different technique. For example, network slicing, as we discussed in the class. We can we can slice the network by end to end and implement this technique. Also, functional split is another technique. And if you discuss about the massive connectivity, like we can use device to device communication. Then new radio air interface. So there are two actually. First one is the non-standalone, and second one is standalone. So non-standalone is basically the first stage of 5G, and is basically using, if you can see from the diagram, new 5G RAN, but existing on a 4G LTE network core. And on the other hand, when you talk about standalone, it uses the 5G new RAN, like the core is also new, and the RAN is also brand new. So when you talk about the non-standalone mobile phone, in this case, our mobile need to be connected to 4G and 5G network at the same time, and the power consumption in this case is very high as compared to like if you talk about the standalone. But on the other hand, like the cost is very high if you talk about standalone, because 5G core is also new. So you can see that like one has some advantage, but another has like disadvantages. So in existing, for example, currently we can say that we only deal with the non-standalone when there is problem, like cost is not a considerable part, then we can consider about a standalone. Yes, when you talk about the spectrum range of new radio, so there are two basically frequency ranges. First one, as you can see, the frequency range 1, including sub gigahertz, and second frequency range is basically from 24 gigahertz to 100 gigahertz. As you can see from the diagram, like for example, the lower frequency is basically used for the wide area. Why? As we discussed in the class, because low frequency can easily pass through the obstacle, through walls and other hurdles. And if you talk about like, it is also like for non-line of sight. Basically, when you talk about the higher frequency, so higher frequency cannot pass through the obstacle and hurdles, and definitely these kind of frequency we use for the line of sight when there is no obstacle between the transmitter and the receiver. For when you are discussing about femtocell, for a femtocell you have inside the room and there are devices connected on the table, you don't need like, there is no line of sight path, so you can use the higher frequency for to benefit from the higher frequency. You can have high data rate for devices which are connected to the, for example, in the femtocell, with the femtocell. Carrier aggregation is a very important technique. For example, in this, like we combine different channel of spectrum for more capacity. As you can see from the diagram, for in case of LT, there is carrier per carrier bandwidth is up to 20 megahertz, and the minimum bandwidth is 1.25. When you combine 5 carrier, which is a carrier aggregation up to 5 carriers, so maximum bandwidth you can utilize up to 100 megahertz. So when you talk about new radio in 5G, so in this case per carrier bandwidth is up to 400 megahertz, and minimum carrier bandwidth is 5 megahertz. So if up to 16 carrier, you have maximum bandwidth up to 6.4 gigahertz. So you can see this technique is very helpful to improve the capacity of the system. Yes, 5G basically support a very large number of antenna on the base station, which we call G Node B. And this large number of G Node B antenna basically coupled with the multiple antenna at the user terminal to help focus energy toward the user terminal. For example, what will be the advantage of this? And you can improve the spectral efficiency. As you can see from the figure, for example, in traditional mobile communication system, there is a beam and whoever the user terminal come into this beam, they can utilize the beam and they are connected, but there are a lot of hurdles and a lot of problems, path loss. And when, if you talk about the second figure, as you can see, new 5G radio figure, there is every terminal has a specific beam, more radial, more focus, more tightly toward, you can say, individual user equipment. And this is also once I do some experiment with the smart antenna, so it will look like a smart antenna. For example, it judges the user terminal and give the specific beam to the user terminal. So by adopting this technique, you can say we can solve a lot of problems. For example, path loss, multi-path propagation, which we face in like due to high frequencies. There is advanced low density parity check code for the new radio 5G. I remember I am doing the project of telecommunication subsystem, making the design the IQ modulator, and I see like when I implement the model like transmitter and receiver, like modulation and demodulation, I see there are a lot of bit error rate on the receiver side. But when I implement with the help of LDPC coding, I see the bit error is reduced very much. So I can imagine this technique is also very helpful to reduce the error in the communication. So in this technique, like you can say, we can use for channel coding for downlink and uplink channel for in 5G new radio, and also how it can be used incremental redundancy scheme like HARQ. Interesting interesting thing in 5G new radio network is basically permit fine grained time deviant duplexing within a single slot. Like what will happen, for example, if that workload is changing dynamically, so the slot organization is changes accordingly. For example, if you talk in this figure, if you see slot aggregation for DL heavy transmission in case of enhanced mobile broadband, so you can see the single slot is divided into two slots. And if you see above, like DL heavy transmission with the first slot, you can also divide one slot. Like slot is adjusted by according to the workload. So this is also another good technique in 5G new radio numerologies. As also this we discuss this concept in the class. As you can see, when you discuss about the LTE, in LTE the subcarrier spacing is around 15 kilohertz, and the time slot is almost 1 millisecond. When you move this network into new radio, so you can see that the 15 kilohertz subcarrier spacing can be increased from 15 to 30 kilohertz. And you can also see in the x-axis the time is reduced from 1 millisecond to 0.5 millisecond. And you can further increase, like from 30 kilohertz to 60 kilohertz, and the time can be further half, like from 0.5 millisecond to 0.25 millisecond. One of the interesting thing, you can see the same amount of information can be sent in half time using twice the frequency resources. The protocol stack in 5G new radio is not that much different from the LTE layer 2. For example, the only difference, as you can see from the figure, like is SDAP, like Service Data Adaptation Protocol. Basically, this is used for mapping between quality of service flow and data radio barrier. And also another part is basically is quality of service flow ID, like when you talk about in downlink and the uplink packet. I have also mentioned some of the like protocol stored functions, like PDCP, RLC, and MAC layer function. I will not go into detail. It's like for example very simple. For example, if you talk about PDCP, it is used for ciphering and deciphering, and MAC is basically, as we know, mapping between logical channel and transport channel. Yes, in the last part of my presentation, I will discuss about the some of the testing or issue we will face during 5G new radio network. For example, over the air testing for at high frequency. When you talk about the high frequency, the antenna aperture is very small, and due to this, for example, antenna radiation pattern is fairly sensitive, and it can be altered due to reflection losses from the surrounding. So when you are going to integrate, you need the test over the air, which is basically include, you need to measure ERIP, effective isotropic gain of the beam, error vector magnitude, and blah blah. So there is a coexistence issue. For example, 5G new radio mid band and high band operate in the same spectrum to like other wireless communication systems. So there is increased risk for sideband interference. And for example, without you need a proper filtering to remove this interference. Otherwise, like for example, there is a lot of interference problem in 5G new radio network. I just show in the like one of the diagram from, I take this diagram from the internet. Like for example, we show there is interference problem in 5G new radio network. Yes, when you talk about drawing the network, the operator has to face a lot of challenges. For example, in terms of new spectrum, heterogeneous network, and especially in the cost. Like you need a big cost to implement this huge network. So one of the possible solution they can use, for example, use the existing 4G network and try to take the advantage of existing network and delay their infrastructure costs as much as possible. Slowly with the time, they can move toward the these new technology. Yes, when you talk about connecting thousands of camera, and when you're talking about smart cities, And when you're talking about conversation AI and natural language processing, you need a new design and business measures. Specifically, there are a lot of work has to do still in this 5G new radio network. Thank you very much for listening. I hope you enjoy my presentation. If you have any question, you can send me an email. Thank you very much. Bye bye.